So now we prove that the definitions are equivalent. Yes. Now so we need to prove two directions, that the first definition implies the other one and the other way around. Now the intuition for the first direction, we just assume the first definition in that direction and prove that the other one holds. So the intuition is that basically all this multi-stories hierarchy which we had, we just aggregate that in those ZIs, the J's. It depends how you call this. We basically aggregate this hierarchy. And the J, let me go back, needed some belief to justify something, and we just can we don't have the depth notion in here explicitly, but we just can take any depth which contains this Sj we need to justify. So for any Sj, we just look at the depth which contains, and then we use that. That's the intuition. Of course, now let us go and concretely prove that. Okay. So give me the first definition, and let's construct the J's and show that they are what we need in the second definition. So the first definition did not take the one which the action which was rationalizable in those xi. So we need to actually in zi add explicitly as I, and those all the xti's or xits, I name it from below above, xits when t goes from 1 to infinity, those are as zi, and so basically it's the union of all those plus si plus what we are calling rationalizable. Anyway, and zj for any other j, we just unite the xj t's for any t from 1 to infinity. Now we now need to prove, since we have that si is in the first condition, si is in zi, we have it by construction, because we construct the dias, the singleton containing I and others, and the other sets. We need to prove that the second condition, for anything which we can take in any j, j being either I or other, whatever, we need to show this thing being justified by some probability distribution formally. Now Sj is either this Si or it belongs to the xjt for some depth t. If it's Si, then, then we define, we assume the first definition that Si is the best response to mu y I, so there is mu such that Si is the best response. So when mu I1 has support, which is a subset of x minus I1, which by the definition of Z here is a subset of those Z. So we have a belief which we need, which has a support in one of those Z, everything is fine. Otherwise, there exists a t which is at least 1, such that Sj is a part of some sjt. J can be I or not here, does not matter. Now, then, by again the first definition, we assume that Sj is the best response to some probability distribution mu jt plus 1, where the support of that distribution is in the corresponding x minus jt plus 1, so in the next step, which is by the definition of our z, that is in the z minus j. So this Sj is also supported by something which has a support in z minus j. So given such a j, a j which is not Si, such an Sj which is not Si, we just take any t that fits here, and we have a corresponding mu j t plus 1 of that Sj. So we've managed to construct Z and prove that all what we need in the second definition holds. Now, that direction, we just begin with the second definition, we solve that, and then we need to construct all these hierarchies. So we just define the hierarchy based on the justifying belief which we are given in the second definition. So 1 second. So assume the second definition, and now let us simply make the mu I1 of the 1 to be the mu I which justifies I, and for any other depth, simply I take the mu which we need from those mu's which we are given in the second definition. The set xjt as defined, as again we mentioned in those parts 2 and 4, which I said they are superfluous. They are, but they actually give us exactly a concrete way to define what we need. And the first definition satisfies the condition, so the conditions that is the best response are satisfied because we took the mu which are best response, which with respect to which those actions are best response. Yes. So the first definition holds. Let me just go back to the first definition so that I can show you this extremely clearly. So we just we define those axes like we noted here in the frame part. And then as I and the others chase being best responses follows from the mu we took, which indeed justified those choices. So we managed to construct a sequence of XJTs and beliefs which have their support in those XJTs such that what we need holds. And of course the beliefs have their support in those XGTs because they have their support in the Z, which may be larger than XGTs. But XGTs define exactly like we need, and define exactly like we need in order to be what to contain the support of both beliefs in 2 and in 4. That's when we define the XJ, these exactly like we want. Okay, so we managed to. That's actually quite clear. So the two definitions are just different by the way we approach that. They're not that different. So the two definitions are equivalent, and now a simple observation. In a finite game, given any mixed Nash equilibrium P, any pure strategy in its support is rationalizable. Now, a rationalizable strategy is defined only for a pure strategy. Because if we look at the mixed game as our original game, then the mixed strategies are pure in that new game. So we can speak about rationalizability of a mixed strategy in this way, but here we are talking about rationalizability with respect to the original pure game, which is finite. We assume it's a finite game, and we just are talking about a mixed Nash equilibrium, and then we say that the original strategies, which are in the support of a Nash equilibrium, they are rationalizable. Now, why? Define, and by the way, that's intuitive. So the Nash equilibria are stronger than rationalizability. It's not only that it's the best response, but it's a best response to what others do. So you exactly know what they do. You are completely consistent. You don't allow like being a best response to something the person does because they think that the other people do that they think, and you just have to be a best response to what they actually do. That's stronger than, generally speaking, that's stronger. So definitely it's intuitive that something which is in the support of a mixed Nash equilibrium is rationalizable. In particular, a pure Nash equilibrium is rationalizable, and that's because the proof is simple. Define ZJs as all the pure strategies such that they are in the support of some Nash equilibrium, of some mixed Nash equilibrium. Now, since every action in the support of a mixed Nash equilibrium is the best response to the others, that we proved such a simple characterization that a strategy is in the support of a Nash equilibrium if and only if, we prove that a mixed profile is a Nash equilibrium if and only if each strategy in the support, it's pure strategy in support, of course, is a mixed response to the combination of that, to the mixed combination of that. And here we use one direction of this proof. So since every action in the support of a mixed Nash equilibrium is the best response to the other mixed actions, the second definition is fulfilled for those J's, and as J's it belongs to one of those. Well, we immediately prove that for everything which is rationalizable. And SI is rationalizable. So any such as J, SI is rationalizable. We call this SI. Any such as J rationalizable, so in particular SI. Let me change this. Change that. Change that. So we define the J. Yes. So now let us look at some examples because these definitions are quite messy, not hard but messy, and that's their hardness, you can say. Sometimes rationalizability yields crisp results despite being quite broad. Sometimes it's strictly broader than Nash equilibrium, but sometimes it yields crisp results. For example, in any case of strict dominance, yes, I've changed this for SI. Now it's SI. So in any case of strict dominance, in particular, let's say prisoner's dilemma, the dominant profile is the only rationalizable profile. So it's rationalizable, of course, because it's also a Nash equilibrium. It's the only rationalizable one, since it's the only best response strategy of a player. Yes, I'm reading what I've written here. It's the only best response of a player. So it is a best response to any distribution. It's trivial to say it's rationalizable, but it's the only. It's rationalizable and it's the only rationalizable thing. Now, in some cases, the results, of course, are weak. So let's look at the pure coordination game. Since we have two Nash equilibria, as we know, top left and bottom right, every strategy is in the support of some Nash equilibrium, of some mixed Nash equilibrium. Now here, every strategy is rationalizable because it's in the support of some Nash equilibrium. Here we don't have anything. Because the equilibrium says that they actually have to be coordinated. It has to be top with the left and bottom with right. And actually, it does not matter, but I would better call it like with the same names even. I would better call the strategies if I want them to be called pure coordination, I would better call it left and right anyhow, but it does not matter. I call it. What I mean is that we don't, rationalizability tells us only that any strategy can be rationalized. That's true. But it does not tell us that there is a story of coordination here. So you see here it's weak, so it does not tell us anything new. I mean, it does not restrict a set of strategies in that case. Okay, so now let us look at a nice example from Osborne and Rubinstein. Let us look at that example of finding rationalizable strategies.